Since 400 BC, it was theorized that all matter was composed of tiny units of indivisible particles called atoms, originating from the Greek word atomos for uncuttable. This theory was proposed by the Greek philosopher Democritus, and was based on logical reasoning rather than scientific evidence. Scientific evidence had not supported this theory until the 19th century. Among the first scientists to investigate the atomic structure was John Dalton, who proposed that atoms were individual spheres with constant density through his billiard ball model of the atomic structure. In the beginning of the 20th century, J.J. Thomson, who had recently discovered the electron, stated that the atom was a positive sphere with negative electrons embedded throughout it, similar in appearance to a raisin bun. Ernest Rutherford, a scientist working under Thomson, set out to prove the raisin bun hypothesis through experiment. Instead, his results and analysis were revolutionary enough to completely refute the original raisin bun model. Our vision of the atomic structure today is largely a result of Rutherford's famous gold foil experiment. So how would one go about revealing the internal structure of anything? For example, if we had a box of a known size and mass, but did not know whether it was filled with wood or inflated balloons. By shooting a series of bullets through it, we would be able to reason about the internal structure based on how the bullet emerged from the box. If the bullets emerged with only a slightly reduced speed and little change to their direction, we would assume that the box was composed of a low-density material, such as wood. On the other hand, if we found that most of the bullets emerged from the box with their original speed but in opposite direction, we would conclude that the bullets had bounced off some very dense material in their paths. Now we can talk about how this concept was used in the gold foil experiment. To reveal the internal structure of an atom, Rutherford shot high-speed alpha particles from a radioactive polonium source at a very thin sheet of gold foil, with the width of merely 400 gold atoms, in vacuum chamber. The gold foil scattered the alpha particles, and the relative locations after being scattered corresponded to tiny flashes of light that were detected by a fluorescent zinc sulfide screen, placed at various angles around the gold foil. The flashes of light could then be observed through a microscope, and the number of flashes at every angle from the polonium source were recorded. While majority of the alpha particles passed through the gold foil with little to no deviation from the angle at which they were shot, 1 in 10,000 were scattered at angles over 10 degrees. On even rarer occasions, some alpha particles were deflected back along their original path. A final result of the experiment was that the gold foil became positively charged after a long period of exposure to the radiation. Alpha particles consist of 2 protons and 2 neutrons bound together, thus identical to a helium nucleus with an overall positive charge. From these results, 3 conclusions were drawn about the atomic structure. From the experiment, most of the alpha particles traveled through the gold foil, thus the greatest proportion of the atom's volume is empty space. And although most of the alpha particles traveled through the gold foil, a few particles were deflected. This evidently showed that the atom contains a very small, but extremely dense central region called the nucleus, which accounts for all of the atom's positive charges and most of its mass. From this information, it was also concluded that the electrons must be in orbit around the nucleus. If the electrons were stationary, they would be attracted to the nucleus, and thus no repulsion force would be exerted on the alpha particles as they approach the nucleus. As the positive alpha particles traveled through the gold foil, very few interacted with the electrons. As a result of their electrostatic attractions, the protons and electrons became bound together, and the electrons are essentially carried out of the foil. This behavior explains why the gold foil became positively charged after being exposed to the radiation for an extended period of time. Upon further analysis done by Rutherford and his colleagues, even more insight was gained into the atomic structure of an atom. For one, it was hypothesized and then further proved that the force that causes the scattering of the alpha particles is consistent with Coulomb's law, which states that electric force is equal to the proportionality constant multiplied by the charge of the alpha particles and the charge of the nucleus, all divided by the square distance between them. It was also proved that it was the charge, rather than the mass of the nucleus, that was proportional with the magnitude of repulsion force between the nucleus and the alpha particles. For example, a nucleus with a great positive charge would exert a great force on the passing alpha particles, while a nucleus with a smaller positive charge would exert a smaller magnitude of force on the passing positive alpha particles. The last observation dealt with the size of the nucleus. An alpha particle has a certain amount of kinetic energy as it is traveling towards the nucleus. This kinetic energy is converted into electric potential energy as it gets closer and closer to the nucleus. When it reaches its closest possible distance to the nucleus, the amount of potential energy at this point is equal to the initial kinetic energy, or the total mechanical energy. Upon rearrangement, the radius of an atom's nucleus was calculated to be 4.2 times 10 to the negative 14 meters. To clarify, this number represents the closest possible distance an alpha particle can come close to the nucleus before it is repelled back along its original path. Through separate calculations, it was calculated that the radius of the entire atom was 1.3 times 10 to the negative 10 meters. The ratio of these two values, raised to the third power, allows us to visualize how much greater the total volume of the atom is compared to its total volume of the nucleus. In everyday terms, if the nucleus were the size of a head on a straight pin, which is about 1 millimeter in diameter, the atom would be the size of a small car.